So today we're going to look at Cantor's diagonalization argument. This is argument fundamental in set theory, and it proves the cardinality, so the measure of size between different sets, are actually distinguished within infinity. So there is a greater infinity and a lesser infinity. So the lesser infinity, the least infinity possible would be the natural numbers, because it is a countable infinity. And the argument shows that the real numbers are actually uncountable, so which means the cardinality of the reals are strictly greater than the cardinality of the natural numbers. So this diagonalization argument can actually be generalized into Cantor's theorem, which is a fundamental result in set theory, stating that for any set A, the set of all subsets of A, so the power set of A, has a strictly greater cardinality than A itself. So for the actual Cantor's diagonalization argument, and not the theorem, we start by considering an interval, open interval, from 0 to 1. And the idea is that since this interval is a subset of R, proving this interval as uncountable would be sufficient to show that R is actually uncountable, since an uncountable set, a countable set cannot contain an uncountable set. So R would have to be uncountable to contain the uncountable set, which is the set of all numbers in this interval. So the proof is done by contradiction. We assume there's a bijective function f, which enumerates every natural number into every number within this interval. So for every number within this interval, 0 to 1, there is enumeration, which we assume to be the function f with a decimal expansion 0.a sub m1, a sub m2, a sub m3, and so forth, where the nth decimal place amn will always be a digit from this set here, so 0, 1, 2, 3, all the way to 9. And the argument is, so here is a drawing of what the argument is actually saying. So for each natural number, there's the function f takes that natural number and enumerates it to some number with such a decimal expansion that is within this interval here. And the key point in the argument is that since this function is assumed to be one-to-one and onto, every number within the interval 0, 1 would actually appear somewhere in this list. So for here begins the contradiction. We define a real number x within the interval with a decimal expansion of a sequence of bn's. So bn is defined as basically the opposite of a and n. So here are the a and n's for every natural number and its function here. So this diagonal here is the a and n's. So bn is defined this way: if it's 2 if a and n is not equal to 2, and 3 if a and n equals to 2. So the bn will always be different from a and n. Say a33 here, for example, b3 and a33. They will always be different by at least 1, because this is a result of the function of the sequence of bn being defined this way. So the point is that if you create x in this construction, that x is actually different from every enumeration of a natural number, right? So x cannot actually be within this enumeration. And the point is that x is a number within this interval that is not cannot possibly be in this enumeration of the natural numbers, and therefore that there is no onto function. That this proves that f is not onto and therefore not bijective, and therefore there's actually no countable. This interval here is actually not countable. So why is x not in this list? Because we assume x to be in the list, but x is actually different from every enumeration of a natural number by at least by at least one decimal place, right? So say if you want to prove that x is not the decimal expansion of the natural number 4, you realize that a_n, which is a44 in this place, is actually different from the fourth decimal place of x by at least one integer that is within the decimal place. So in general, x cannot be f1, x cannot be f of 2, and because a_n and bn will always be different by decimal place. So x cannot be equal to f of n for any n within the natural numbers. So there is a x within this interval outside the range of f. So this means f is not onto, and it's a contradiction of what we started with, which was that f is actually a bijective function. And this contradicts the assumption that this interval from 0 to 1 is countable, and hence r is actually not countable also, because this is not countable. So some important notes within this argument, some less obvious points, if you will. So the important point to note is that including the x which we have chosen to not be within the enumeration of the natural numbers in the range of f, so defining some new functions such that this is actually included in the enumeration will not actually affect the diagonal argument, because if we assume that, say, some new function g of n does exactly the same as f of n, but it actually has x within its range, it will also appear somewhere in this list. And we can define a new x such that the new x will have its decimal expansion at the nth place, bnn, be different to the old x with its decimal expansion at bnn by one decimal place. So if the old x had a decimal expansion of bn equals 2, then the new s would have a decimal expansion at that decimal place of 3. And so no matter if you decide to include x or not, there will always be a number which we can prove is not within the enumeration. And another possible point of query could be that since the rational numbers also have decimal expansions, the diagonalization method could be used to prove that the rational numbers are uncountable, because this process here essentially proves that whatever set is being listed here is uncountable. So it could prove the rational numbers are uncountable. But we can actually get around this argument by saying that all rational numbers have some terminating decimal expansion. And in this argument, we're only required to choose the most convenient expansion we like of a rational number. So we could just choose a terminating rational number, and then the guarantee that the function which the sequence which we define to be Bn, the guarantee that Bn will be different to An does not exist anymore. So if it's actually with rational numbers, this argument would not hold. And this also clarifies the case for numbers with multiple decimal expansions. So you could say a half is worth 0.5 and 0.499999. So eventually this terminates, and this just shows that the rational numbers are actually countable. You can't use this argument to prove the uncountability of the rational numbers. And yeah, so this result is pretty important for set theory. It's a fundamental result, and it again, to recap, it generalizes into Cantor's theorem, which is very important within set theory, because I think I might need some more courses to figure that out, because why? But there you go. Thank you for listening.